Hello again, everyone. This is page 2 from the central net force packet. I redrew the picture here so that I can reference it. Hopefully it's good enough. So I want to start with number 7. So at point A, the cart is moving at a constant speed in a loop, which is a part of the circle. So draw a qualitative force diagram. So again, qualitative meaning there's no numbers, just sort of what is happening. So here's A. Kind of the same sort of situation we've been going through. We're ignoring friction on a roller coaster, and there's nothing accelerating it. So the only forces are gravity pulling the cart down, and normal force, which is pushing up. And this isn't really addressed until part B, but because it's going in an arc this way, we know that the central net force has to point towards the middle of the circle. So that means that's where the direction that gravity is pointing. So then normal force is going to point the exact opposite direction, and it's going to be smaller, which is addressed in letter B. Are the forces balanced or unbalanced? They are unbalanced. And you don't have to put this, it doesn't ask, because it is going in a circular motion. And so the net force is pointing down. Another way you could say that is we could say the force of gravity is bigger than the normal force. You don't have to put both things. Either would be fine. 8. So here's where we actually get into numbers and doing some calculating. So at point B, so we're here. This is part of a downward curve. So the central net force is pointing down. This is part of an upward curve. So the central net force is going to point up. So we got some numbers. Radius is 13. Normal force is 2,400 newtons. So draw a quantitative force diagram for the passenger with a mass of 60. So A, because the ground is underneath, our normal force is going to point up, and this one's quantitative, so we want to actually include the numbers. And then gravity is pointing down. Kind of the opposite direction of this one. Well, we don't have to actually know this beforehand, but gravity is just going to be that same equation that we always use, mg, where m is our mass, which is given. I'm just going to kind of write it at the top. Mass is 60 kilograms. So 60 times 10, which is 600 kilograms. Or sorry, not kilograms, but newtons. My eraser's trash, so I'm not going to try. So 600 newtons. And just kind of a double check, since it's an upward curve, we know that the forces are unbalanced and our net force should be up. Which means when we sort of subtract our forces, what should be left over is positive. So 2,400 is up, and 600 is down. So the up is winning. So that kind of makes sense. What is the centripetal force? So that one is just the difference between the forces. We have an upward force and we have a downward force. So the centripetal force is the net force, which is the difference. So net is going to be 2,400 minus 600, which is 1,800 newtons. How fast are they going? So that's where we're going to use our mv squared over r equation. If this is going to work out, we're looking for v, so we need to have everything else. F is the force we just calculated, which is 1,800. Oops. M is still 60. V is what we're going to find. And then R is 13. So to solve that, I just got to multiply by 13 on both sides, which I can't do in my head. So we're going to calculator this. Oops. So 1,800 times 13 is 23,400. And then I got to divide both sides by 60. 390 equals v squared. And then I have to turn it sideways to square root. So that button, when I square root both sides, velocity is 19.7 meters per second. And I'll just do 8 on the next page. Oh, sorry, 9. That was 8. The cart is traveling in a radius of 7 meters, with a speed of 12 meters per second. So that's at this point. And an interesting thing to note at point C is gravity is going to be pulling the cart down, and then the track is above the cart. So the normal force is actually also going to be pushing down. So draw a quantitative force diagram. So gravity is pointing down like it always is. So I'm going to just say Fg equals 600. And we calculated that in the previous problem. It's again just 60 times 10. And then the normal force, the track is also pushing down on the cart, which is kind of weird to imagine, like nothing's holding the cart up. But, you know, that's just kind of what happens in a roller coaster loop. When you're looping up, you just, if you're not going fast, you're just going to fall right off. So the speed is what kind of keeps it going. But the normal force is also something pointing down, but we don't know what it is. So to find out, we're going to find the net force, which is our same mv squared over r equation. And we should have like 60 v and r. So we have all the things. So I'm just going to, again, calculator that. So 60 times 12 times 12 divided by 7 is 1, 2, 3, 4. That's neat. Let's say 0.3. So that's our net force, which means the combination of all of the forces pointing down are 1, 2, 3, 4. So 600 of that is coming from gravity. So then therefore the normal force must be that minus 600, which is 634.28. 0.3, whatever, that'll work. So then that's kind of your answer.